Good morning, all of you. Welcome you all for the 1 week FDP on computational methods in boundary theory, day 5. And today's first session topic is efficient augmented. First session topic is deep learning neural network for approximating the solution to differential equations by Professor SM Mallikarjunaiah.
First session topic is efficient augmented. First session topic is deep learning. Deep learning neural network for
I request Dr. SM Mallikarjunaiah to continue the said lecture, sir. Please, sir, please continue your lecture, sir. Thank you, sir.
Thank you. Thank you very much for this opportunity to present my ideas on coming up with new methods and approximating solution to class of differential equations. And I see that this FDP is on computational methods in boundary layer theory. So what I did was I picked up examples related to this FDP. Okay, so the method is fairly simple and very easy to implement, but let me go ahead and explain the method. First, I have to acknowledge a couple of things. Computations for this project are done on our computing cluster, supercomputing cluster in our university. I thank them for providing all the necessary infrastructure for myself and also for my students. Okay, and second, thanks to my university for the generous financial support for this research. Okay, now this particular research actually grew out of from my master thesis students' work. So basically what I'm showing today is part of it done by my students and part myself. Okay, now, as we all know that recent years, there have been a few buzzwords going around in academia as well as industry. The first buzzword is like data science. So suppose if you put this word into Google Scholar, it's going to tell you that overall around 80 lakh research articles, monograms or textbooks have written with the keyword data science. Okay, out of it, more than 24 lakhs papers have written in recent years. And the next buzzword is deep learning. Okay, now you do the same thing, put this to Google Scholar, it's going to tell you that there are 57 lakh some number of papers have been written with the keyword deep learning. And then machine learning. Machine learning also is another buzzword, and that counts around 50 lakh papers. Now, for mathematicians, there are excellent scope working in these new areas because these are all, I mean, some of the theorems and classifications were done before, but then the applications wise, there have been, I mean, there are a lot of scope for mathematicians to explore. Okay. And then let me tell you outline of my talk today. I'll give very brief introduction about artificial neural networks and especially the architecture that I am going to use for today's talk. And then I'll also show you how one can use the networks as an approximating tool to for the solution of differential equations. Okay, so we can compare this with our traditional discretization techniques like finite element, finite volume, difference, and all other methods. And then the question is, why neural networks? Because neural networks actually works better as answer functions. Okay, answer means you know them a priori and then put them into your differential equation and find the coefficients. And that is not new. That is not new for us, right? We have been doing that in many other techniques, like even Galerkin method, weighted residual method. All those methods were based on the same principle. So this neural network is also not that different. Okay. And then I'll show you a few classical results, theorems that suppose the work of using neural network as approximators or approximating tools, and also some very brief few things about optimization. And then I'll show you some numerical results. I've selected two test problems for this talk that are related to boundary layers. And then I'll also discuss about benefits and drawbacks of ANN, artificial neural networks. And then I'll also tell you about like what are the remedies, or finally I'll give you a message to take away from this talk. Okay, now the fundamental architecture of artificial neural networks look like this. The picture on your screen, the leftmost layer, we call it as an input layer. Now this can be a vector, just a single vector, or combination of vectors. Okay, the rightmost vector, the rightmost layer is called the output layer. Again, this can be a scalar quantity or a scalar quantity at vector positions. Okay, now in between we call them as hidden layers. Now in this figure, I've used two hidden layers. Basically, you can just have one hidden layer. Okay, now we also have something called weights associated between each layers, starting from leftmost, which is the input layer, to the rightmost, which is the output layer. And each of the hidden layers, they need what is known as biases. Okay, now what are biases? Later on I'll explain. Now if you look at this network, now the thing that we need to have some information are about the weights and then bias. Okay, now the thing is, now if you look at this, how do our differential equation or obtaining solution to differential equation fits into this architecture model? Okay, now surprisingly, what we were trying to do before by using standard numerical techniques of obtaining or approximating solutions can be easily turned into an optimization problem. Okay, and you can use a network model to obtain the parameters that can define the solution. Okay. And then a very brief introduction about neural networks. Okay, so let me tell you some basic notations. Let D is the input dimension, X is input vector. Okay, and then M is the number of hidden layers. Now the first layer, we call it as layer 0, that's the input layer, and the last layer, which is the mth layer, is the output layer. The m-2 layers that are in between are called hidden layers. Okay, now every layer except the first and the last, there are what are known as neurons stacked one top of each other. Okay, now they receive information from their previous layer and they pass information to their next layer. Okay, Now the information that they get is only in one direction. Means suppose if you look at the second layer, now it can only pass on to the information to the next layer, third layer, not to the first layer. Okay. Now there are networks that can also do the both ways, both forward as well as backward. But in this setup, we don't do that. We don't do the backward. Okay. We only supply information in forward direction. That's why it's called feed forward neural network. Okay, now rho is the nonlinear activation function. I'm going to tell you what is that. And the multi-dimension vectors called W1, W2, W3, they're called weights. Okay. And B1, B2, B3 are called neuron bias terms. Okay. Now we need bias and weights even to get the output layer also. Okay. That's why we needed three sets of weights and three sets of bias. Now weights can be matrices. So multiplying weights with the information in each of the hidden layer, especially in each of the neuron, is like the matrix scalar multiplication. Okay, and the vector, if you look at one vector of weight, now that consists of weight from the previous layer, pass it on to the next layer. That's why it's written as m comma n. Okay. Now, as I was saying before, it takes information from its left side and pass it on to the right side. So that means it needs to know the neuron information of its previous and as well as the next one. Okay, and sigma k is the linear affine map. Okay, and then the output input formula or input output formula for any network is given by this equation number one, where here, if you think of it, I mean, if you think equation one, this is like a functional operation. So this functional takes vectors as input and it spits out vectors as output. Okay. Now, as I was saying before, WK are the weights. They can be matrix. X is the input vector and B is the bias vector. Okay. Now here, the xi, the set xi, that is a set that contains the information about the network parameters, tunable network parameters, which are the weights and bias. Okay. Now this is the formula that you can think of for one layer. Now, if you have more than one layer, you can think of the same function acting successively for each layer. Okay, activation function. Now, why do we need activation function? Now, in each neuron, when we do calculations, the values may vary a lot. Okay. Now we want to bring them probably between like 0, 1. And so for that, we need to act a function on each neuron, and we use what is known as sigmoid function, which is the one that is used a lot of times in this type of setting. And the graph of sigmoid function is this. As you can see that whatever could be the input, x is its input, and now it's here the scalar quantity. Now the output is always between 0 and 1. Okay, which is depicted in the blue line. Okay, now we need to act the sigmoid function. As I was saying, this is not the only one. There are so many other activation functions are available, and it's been like dynamically developed. Okay, and so many, I mean, not all problems you can use the same activation function. So this is also problem specific. And the question is, why neural networks? Okay. Now, neural networks, these the fundamental concept is not new. It's pretty old concept. And if you really think about it, it's actually the linear algebra. Okay. Now, why they're important? Because of their universal approximation property. Okay. Now, this was independently investigated by many researchers. So I'm going to name two very important two names, Sibinko and Harnik. Okay. Now I'm going to show a work of Sibinko, and this is the fundamental theorem for any approximation that you can do using neural networks. Now, what does it say? Now, if you think about the sigma cap be any discriminatory function, I'm going to tell you what is discriminatory function means. Then the finite sum, which is given in equation 3, is dense in CFIN. Okay, where in other words, you take any function f in CFIN. I'm going to tell you what is IN also. So next slide, I'm going to tell you what is sigma cap, which is discriminatory function. I'm also going to show you the definition of or the meaning of IN. Okay. Now you take any function f in CFIN. Okay. You can write that f as finite sums by using a formula 3. You can take that as a formula 3, and the difference between that in some specified norm, okay, will be a small number, and this is true for all x in IN. Now, this theorem has been written independently by several authors. Even Harnik also has similar theorem, and nowadays everybody calls this as universal approximation theorem. Okay, for neural networks. Now, if you look at it here, your sigma cap. Remember, we already saw in our input-output formula, we saw that as the activation function, right? As a linear map. Now, IN is n-dimensional unit cube, okay? And CFIN is a space of continuous functions on IN. And then sigma cap is, as I was saying, it's called discriminatory function. What is that? It is if for a measure mu in M of IN, M you can take it as space of Borel measures. Okay, the integral over all IN of this sigma cap, the Borel measures, is equal to 0, and such functions are such mappings. They are called the discriminatory functions, and this is true for all y in Rn and all other inputs, theta and x in Rn and R. Okay. Now what does this say? So this theorem says, give me 1 second. Now this theorem says if you take any continuous function and you can approximate that by finite sums. Okay, that's the very basic understanding of this theorem. Okay, now that's the fundamental basis for approximations using neural network. Okay, now this sigma cap, okay, is also called the sigmoidal. Okay, it's 1 as the argument goes to positive infinity, and 0 and the argument goes to negative infinity. Okay, now one can easily map this, and then you can also compare with the input-output formula that I gave before. Now, how do we use this? So I'm going to show you 2 examples in this talk that are closely related to the FDP. Okay, I'm going to illustrate the approximation capability of a neural network by following examples. I'm going to solve a SPDDE, singularly perturbed delay differential equation. And as I was saying, since the FDP is on boundary layer theory, so I took a differential equation ODE basically that has a boundary layer behavior. Okay. And also I took an example from fluid mechanics, okay, which is approximating a coupled third order nonlinear differential equation that arising from modeling factor scan type of flow of nano liquid over a moving wedge. Okay, so I'm going to show you the approximation using neural network for these two cases. Now we have done several. We have done the fifth order, sixth order nonlinear, linear ODEs, and also we have done up to ninth order ODEs. Okay, and we have also done partial differential equation also, and we have done even integral equation also, Volterra integral equation also. Okay. Now let's look at the first example. First example is the SPDDE. Now we'll consider following type of SPDDE, okay, with layer behavior. Okay, so the system is this, okay, L cap of y epsilon, okay, is the first equation, and the boundary conditions are equation 2 and equation 3, and omega I'm going to consider the since it's ODE, I'm going to consider the 1D between 0 and 1. Okay, now this problem has been studied extensively by several authors. People from IIT Kanpur and IIT Warangal have done a great amount of work, and they have come up with the finite difference methods, finite element method, tools as approximating such behavior. Also, people from IIT Guwahati. Okay, now the parameter epsilon has some special meaning if you look at where these problems are arising. Chemical physics, basically. Now it's actually between 0 and 1, but it's close to 0 than 1. Okay. Now delta here is a delay parameter. Now, if delta is 0, then you don't have a layer behavior. It is a classical second order singular perturbed equation. Okay. Now there are basically several methods available. Okay, and also delta is also small number. It can be 0, but I mean, it's far away from 1, but close to 0. Okay, now here the functions A, B, F, and alpha, they are smooth functions, and beta is a constant. And then further, we need to assume that the BFX, this function BFX is greater than some number gamma, which is a positive quantity for all x in the closed interval 0, 1. And then it is clear that from this equation, there will, as I was saying before, there will be a boundary layer behavior, either on the left side and the right side, depending on the value of delta and also the sign of A. Okay, so the question is, the naive Runge-Kutta type of method cannot approximate when epsilon is really small, like of order 10 to the -2, -3, etc. But you have to come up with a special type of mesh if you want to use just Runge-Kutta, or if you want to come up with finite element, then also you need to come up with special type of mesh. But for neural network, we do not need all those. I'll show you later. It's a pretty straightforward implementation. Okay, as I was saying, the delay term can be up to some order. So what we should do is, instead of just directly solving this ODE, I'm going to expand this y prime x minus delta, okay, up to an order of delta. I mean, we can keep expanding up to delta square, so that when delta is really small, delta square is negligible. So if using that fact, we can rewrite or reformulate the previous boundary value problem what we saw by adding that delta A to the y double prime. Okay, and then you now see a second order ordinary differential equation, but all the layer behavior and parameters are attached to the second order derivative. Okay. And as I was saying, it is clear that the approximate solution is of order up to delta. Okay. Now, remember, our goal is to find a numerical solution or an approximate solution to this BVP, right? This BVP. And the important parameters are epsilon delta. And most importantly, it's epsilon. You will see that the solution behaves like, the solution depends upon epsilon. Okay. Now, as I was saying, when I showed the picture of neural network, the goal is to approximate the solution to the differential equation by this kind of architecture. Okay. Now, basically, we need to find two parameters, that is the weights for each layer and the bias that goes into each layer. Okay. And those are the network parameters. Okay. Now, to do that, as I was saying, we need to find an optimal parameters. That means there's some kind of minimization is involved, right? So that means we have to come up with what is known as loss function. Okay. Now, traditionally, if you have a closed form solution, means suppose take for example, I have solution y epsilon that satisfies the differential equation along with the boundary terms. That means I now have closed form solution on my hand. Okay. That way I can check if I plug that into my left hand side, it should give me right hand side f. Okay. Or if I move f to my left hand side, then it should give me the entire left hand side equal to 0. Okay. Now the idea is that. So let's come up with, by using that idea, let's come up with the loss function. Now there are many other ways of coming up with the loss function. What I am using here is the root mean square kind of loss function. Okay. Now here the loss function I'm going to denote by the symbol L, the script L of y cap. Y cap is my approximator to the solution y epsilon. X is the input, and the set xi. Okay. And the set xi contains all the network parameters, means weights and bias. Okay. Now I'm going to define my loss function. That's my loss function L. So I'm going to minimize that, optimize that for my, by varying the network parameters W and B. Okay. Now that is how the idea of using neural network to approximate solution to differential equation comes in. Okay. Now instead of satisfying the f of x absolutely, you move that f of x to left hand side and do kind of a root mean square or an L2 type of loss function. Okay. Now that's exactly is what I call it as loss function that's given in the last equation. And now if you look at this carefully, the blue terms, they're all coming from the differential equation, right? You see epsilon delta a xi. So think of xi's are input or xi's are the discretization points in your domain. And you know epsilon, you know delta, that they are given. N is the number of samples that you take, means number of points you take between 0 and 1. Okay. Now, since y cap epsilon is my approximation to solution y epsilon, so I'm going to replace that to the differential equation, move f of x to my left hand side. I take a root mean square kind of loss function. So the blue term coming from differential equation, the red two terms come from the boundary condition. So that is what the difference of this approach compared to other approach in the literature. Means I want my solution not only satisfying the differential equation, I also want my solution or my approximation to satisfy boundary conditions. So I'm forcing my solution to satisfy both. Okay. Now, some other studies, they do only for differential equation and they adjust the parameters so that they can satisfy the boundary condition in some sense. Okay, not exactly the root mean square, maybe the absolute difference. Okay, now I added the boundary terms also. The two terms I've written in red, I call the entire thing as my L, which is the loss function. Okay. Now, as I was saying, N is the number of sample data, training samples. Okay, now that's exactly the procedure. Okay, so you have a loss function on your hand and you put that into the optimizer and you minimize that. Okay, minimize means what? Minimize the overall error here in the loss function, and you adjust your weights and bias so that you get the loss function close to 0. Okay, now remember, this is again a numerical technique. You won't get exactly 0, you get something close to 0, and we have to satisfy based on the computational cost we want to expand, and also based on the available facility what we have. Okay, now let me show you the overall algorithm. Overall algorithm is this. The first line is input. You choose the parameters for your differential equation, means epsilon, delta, alpha, beta. And you also choose the network parameters, means you choose number of hidden layers. So remember the universal approximation theorem that I showed few slides before, it didn't tell us anything about number of layers. So for the, if you closely look at the proof given in Sibenko's paper, so it does not matter how many layers you choose, okay, or how many neurons in one layer you choose. He says if you choose sufficient number of neurons, you can approximate the solution. You can approximate any function with a finite sum. Okay, so but then we want to do what is known as deep learning. That's why we choose more than one layer. And also we choose number of neurons in each layer. You can take it like 8, 16, 24, etc. And you also choose maximum number of iterations. Iterations means what? Iteration you are spending on the minimization here. Okay, you can say that I don't want to go above like 10,000 iteration. Okay, and then number of points, training points. This I'm going to show you. We do it in an adaptive way. And training rate means whenever you take your first instance, you see how far you are from your right side, and then you can fix the rate based on that. And also you set an activation function. Activation function is already fixed, which is sigmoid function. I showed that in a few slides back. And also you choose an optimizer. Optimizer means we need a method to minimize the overall loss. You can choose any good quasi-Newton method. Okay, in MATLAB, in all other platform, Python, they're all implemented. We don't have to implement them by from scratch. We can just borrow them and use it in our algorithm. Okay, now the step 4, discretize the domain. Domains in our problem, it's 0 to 1. Into 2 to the s number of subintervals. Okay, s is you choose maybe 4 subintervals. Take it s equal to 2. Okay, in the first instance, and then create a training data. Means this is the vector of data points between 0 and 1. Okay, and then our algorithms goes into a loop. You do this all steps 6 to 9 if you don't satisfy the maximum number of iterations, or your overall loss is larger than some small number. Okay, so we usually fix 10 to the minus 6 as my number to stop this iteration. Okay, you could choose even more than that. Then if you choose, I mean, less than that, 10 to the minus 6, less than 10 to the minus 6, then we may have to increase number of iterations, or we may choose number of neurons, more number of neurons, or maybe more number of hidden layers. Okay, now train your network using the data created previously and compute the last function. Last function is given here in this previous slide. You compute that, okay, and then create a new data set taking twice the number of points you took previously. Okay, if you have taken like 4 points, now take 8, now take 16, like that. Unless you don't satisfy this condition given in line number 5. Okay, and then suppose if you satisfy, then whatever previously you have computed, the network parameters, means weights and bias, you can use them for the remaining number of iterations. You don't have to update. Okay, when you come out, whatever the last trained solution, you call it as your network output, or you call it as an approximate solution to your differential equation. Now, basically, the same algorithm works if you're doing a ODE, PDE, integral equation, or integral differential equation, things like that. Okay, with very minimal change. Okay, now what we did here, we have implemented this. Okay, and then let us see. Now let's take an example. I'm going to take this example given in equation number 7. Okay, I took 0 as my right hand side. I took a second order SPDDE with layer term delta, and I took the boundary conditions also given in the last 2 equations. Okay, now I do like I did before. I'm going to expand y prime x minus delta so that I don't keep that delay argument like that, x minus delta. Okay, so I expand and then I get a new updated boundary value problem, and that look like this. And you see easily that this delta is added to the second order term. Okay, and then equation 8 or setup 8 is what I want to solve. So I have a second order delay differential equation. It has both epsilon and delta, and I have some boundary condition. Okay, y of 0 is 1 and y of 1 is 1. Okay, good. Now the goal is to find the approximate solution to equation 8 using our neural network. Okay, now what we were saying before, clearly this is layer behavior at x equal to 0. If you look at the first boundary condition, it's clear that this is a layered behavior at x equal to 0. What does it mean? It means if you take smaller and smaller epsilon, you will see that it creates a boundary layer near 0. Okay, now since it's a second order homogeneous differential equation, we can actually compute the solution by hand. Okay, now I took an example so that we can compute by hand, and it's easy for us to compare. If we compute by hand, equation 9 is a solution. Okay, and where m1 m2 are given by last but one formula, and c1 c2 are given by the last equation. Now you have exact solution, satisfied both differential equation as well as the boundary condition. Okay, now let's put that into our network method and then see what the solution is like. This is a solution. If you go from your leftmost figure to rightmost, I kept epsilon equal to 1 in all the 3, but I'm increasing delta. I take 0.01 to 0.03 and 0.06. Solution did not change much. And I also did taking epsilon equal to 1 and delta like 10 to the minus 12, and solution did not change much. Okay, that means what? That means our delay parameter does not affect much. So in our next simulations, we can keep that fixed. Let's keep it some small number, 10 to the minus 3, but let's reduce epsilon, and you will clearly see the layer behavior. Okay, now this is for epsilon 0.5 and delta 10 to the minus 3. And that's for 0.1 delta 10 to the minus 3. You see both exact solution, which is the dark black line, and our solution obtained from our neural network architecture, which are this green dots. Okay, and we could compare the error and other things. And I reduce epsilon more, and you see the solution is close, moving towards x equal to 0, which clearly creates a boundary layer near 0. And that boundary layer, we can estimate actually it is of length epsilon. Okay, and then I reduce more. I took 0.005. Okay, and that's a solution. And our approximation method still works pretty well, and we can keep doing it. Okay, so that was example number 1. Now let's look at example number 2. Example number 2, as I was saying before, since it's FDP and boundary layer theory, I took one example which is from this paper by Mahantesh and others, including myself, okay, which appeared in ICHMT in 2021. Now the model basically is flow over the moving wedge. Okay, you have a fluid with some velocity and the wedge also moving with some velocity, and you can write conservation laws for this set of nonlinear partial differential equation. And since you are interested in computing the boundary layer behavior of the solution, so you can come up with a similarity transformation and reduce the model partial differential equation to coupled nonlinear ODE system. And the interesting thing here is to study the velocity and the temperature. Okay, but we don't compute the velocities directly, but we compute them with some other parameter. Okay, now all the details are in this paper. Okay, I'm not going to show all those details, but what I'm interested in taking this third order coupled nonlinear ODE and then put these two into framework of neural networks. Okay, and then see and compare whatever the solution we got by using standard Rangekutta type of technique. We can compare the solution obtained from neural network with one that's published in that paper. Okay, and all the derivations, as I said before, are in that paper. But our goal is to approximate solution to equation 10 and 11 subjected to boundary condition 12. Now if you carefully look at equation 10 is actually third order nonlinear ODE, but does not have temperature variable there. So that means you can solve 10 uniquely, means you can come up with a loss function for 10, like the way I showed before. You can also use the boundary loss. Now in the boundary loss, you have f prime 0 equal to some lambda, which lambda is a known constant, okay, parameter. And then you also need to impose f prime at infinity equal to 1. So you can choose infinity means sufficiently large number, large interval, maybe 0 to 30, maybe 0 to 50. Okay, so our goal is to solve 10 under the subjected to conditions f of 0 equal to 0, f prime 0 equal to a constant, and f prime at 30 equal to 1. Now there are two ways that you can define loss function. Now remember, the last time I showed you, the loss function did not involve any Neumann type of boundary condition. It's all plain and simple Dirichlet condition, right? Plain and simple Dirichlet. So that you can impose them like you're imposing using strong solution. Okay, but if you want to impose Neumann type boundary condition, there are two ways of doing it. One, you can impose explicitly. That means you compute the gradients of the network parameter and then use that in your loss function. Or that's one way. The second way is, instead of computing derivatives for the network parameter, you use a finite difference method. To approximate f prime. Okay, because finite difference means now it is almost like a directly bounded condition, so then you can easily accommodate like the way I showed you before. Now you do both the ways, you end up in getting the same answer. Okay, so not much difference. And then once you know solution to equation 10, f at every point, data point between 0 to 30, okay, use that f here in the equation 11. Now you have a second order linear differential equation. Now these are all constants, okay, that come out of model, and all those are given in that paper. So 11 is much easier differential equation. Okay, this is one way. Or you can also iterate here 10 and 11, and you can come up with just one loss function. Creating a vector is like f is its first argument, theta is a second argument. So use that and define a loss and minimize that for that vector of f and theta. Okay, you can do that way also. Now, any way you do, you get the same answer. Okay, now let me show you. Now that's the solution we've obtained. The red line here shows the reference solution, means the solution obtained in that paper. And the green dots are our solution obtained from our network architecture. And this is the plot of f prime, not f. Yeah, that's a plot of f prime. Okay. And then theta. Okay. So we stopped 3. Okay, actually we did up to 30, but for the plotting purpose, I only use up to 3 because it's already 0 there. Okay, now that's a solution for theta. You see that we closely retrace that line, means the solution obtained using standard Rangikuta type of technique. Okay, now what does this show? This shows that our network architecture method can be used as an approximation tool for a certain class of differential equations, right? Now let's list out some benefits. Okay, now benefits are, number one, you can only use small neural network, means if you just use one layer, 8 neurons, that is perfectly fine. You can obtain the loss of 10 to the minus 8, minus 7, like that. Okay, are you able to approximate solution to differential equations? Now the algorithm is very easy and easy to simple and easy to implement. And then these ANNs, artificial neural networks, they can able to handle BVPs in complicated domains also, and even higher dimensions. But if you devise any other numerical method, you have to devise as a dimension dependent method. Okay, now this is almost like a dimension independent. I say almost. And then now no need to worry about choice of approximation spaces. Now approximation spaces means, if you remember my previous talk, I gave a talk on finite element method, and I did solving a Navier-Stokes kind of problem. Now for Navier-Stokes or variant of Navier-Stokes kind of problem, when you want to approximate velocities and pressure, you need a 2 different approximation space. Okay, that means what? That means creating shape functions is a headache. But here, all you do is you just create a loss function. That's all. You just create a loss function and minimize that. You do not need to worry about creating approximation spaces. Okay, now we also did Darcy and Darcy-Brinkman equation also using the same kind of method, and we tested that against some known solution in the textbook and matches very well. Okay, now these are some of the benefits. Now, on the other side, there are some limitations. I don't call it as disadvantages, but there are some limitations. The fundamental limitation, as we are all mathematicians, we look for proofs, right? We look for proof for convergence. That's the most fundamental that should come out of any numerical method or any method by that fact. Okay, now the proofs are very rare. Okay, nowadays there are some proofs available, but not all. So the plenty of opportunities for mathematicians to explore. And then for some stiff problems, okay, the optimization requires huge number of iterations. Means there is already a scope here to come up with a better optimization techniques for stiffer and stiffer problems. Okay. And then now it's not that clear how to utilize the ANN based on approximation method for many other multi-physics problems. For example, if I want to study heat transfer problem, so I want to compute velocity, I want to compute pressure, I want to compute temperature. So there it's not that pretty clear. Okay, so it's still in the baby level. And then more importantly, there is still not a clear argument about the optimal network parameters. Means how many number of layers I need to achieve to see certain convergence rate, and how many number of neurons I need to see certain convergence rate. Now, if we look at the universal approximation theorem, it just says if you use one layer and sufficient number of neurons, I say sufficient number of neurons, you can get a good approximation. Okay, that's not clear. Now, nowadays, there are some proofs, there is some improvement in this direction. Some proofs are available about especially choosing right activation function and getting a convergence proof, and also coming up with some optimal values of the parameters. Okay, these are some limitations, but this should not stop us exploring this method. Okay. The takeaway message is ANNs have great potential, okay, as a support for standard discretization techniques to solve class of differential equation. Now, we always look for whether my method is a faster or not. So one can couple the machine learning or the artificial neural networks with standard finite element, and you can come up with a hybrid method that can give you the solution in a faster and also keep up with the convergence rate. That's possible, and there are some papers, very recent papers are available in that direction, but there are like plenty of open problems for any one of us to explore. Okay, with that, I'm going to stop. Thank you for this opportunity.
Yeah, thank you very much, sir. Good morning. I had a class in the morning, so I was not there in the morning. My colleague was there.
Sure.
So I joined in between, and I could really, follow what you completely gave a lecture on.
Thank you.
And it was very
that will make me happy
to know that ANN can be used even to solve a coupled differential equation, that to non-linear as well.
Yeah.
It is not doubt. My
Sure.
thing is it like here we are coupling the decoupled system of equations to get a total loss function and then solve the given system?
Yeah, wonderful.
In general, in mathematics, what we do is we decouple the coupled and then we go for solution system of equations. But here we did the other way. Is it the case actually?
Yeah, you can do both ways. You do not need to decouple. You can actually come up with one loss function.
Yeah, that's not actually coupling. Decoupled equations you have coupled. I mean, you have made it one equation, right?
Yeah, but this boundary value problem came from one study, so I
Okay.
did not do anything. So I actually took this because it's the FDP is boundary layer theory.
Yeah. Okay.
So that's why I took this. Otherwise, I wanted to show you Navier-Stokes. I wanted to show you some 9th order differential equations, 6th order
Yeah.
differential equations, as well as
Okay.
PDE, and also we also did it for Fredholm second kind singular integral equations.
Okay. Okay.
So varieties of problems we have solved. I mean, all these have been done by my master students.
Okay. The main essence of this ANN is to get a total loss function, right?
Yeah, absolutely, absolutely.
Okay.
And all you spend your time,
Yeah.
especially intellectual time, is coming up with the loss function.
Loss.
And it's not that difficult. You just take the differential equation
Okay.
and you come up with a root mean square. Root mean square is easy because by using the optimization idea, we can also prove root mean square is the best one.
Okay. And again, the
So
second question is, how do we choose the weights?
Okay, that comes from the optimization. W and B, the weight, only the first iteration, you choose it by some standard technique.
Okay.
And later on, it comes from the optimization. That is exactly what you are obtaining from the optimization procedure, weights as well as the bias.
Bias, yeah, bias.
Yeah.
And then
And
the
you
number of
call
hidden
both of
layers.
Yeah, number of hidden layers we choose, like the user choose. So
Okay.
if you want, you can just have one layer
Okay.
with some like 500 neurons.
Okay. Okay.
And then it works pretty well.
Okay.
I just did one layer, 8 neurons for these
Okay.
two
Okay.
sets of problems that I discussed.
Okay. Very much thankful to you, sir. It was very interesting talk, and I hope we'll continue to keep in touch and have an association to continue some work in this field.
Sure.
Because I'm also interested very much in this particular ANN or machine learning or deep learning for solving a differential equation which arises in our fluid mechanics.
Absolutely.
I hope we'll continue our association to work together.
Sure.
I really thank from the bottom of my heart and our department for you to spare your time and share your deepest knowledge on this ANN.
Absolutely, my pleasure. So thank you for the opportunity, and also thanks to Dr. Vijay Kumar sitting next to
just
you.
beside me. He's
Sir, thank you, sir. Thank you for your accepting our invitation.
No formality, please.
Yeah. Sorry for not able to attend your sessions.
That's fine.
You can continue your relation in future also.
Sure.
Thank you, sir. Thank you very much.
Sure. Thank you.
Thank you, sir. Have a nice day.
Thank you.